So, ladies and gentlemen, yes, we're going to go back right to the 17th century. Will you please welcome Robert Boyle?
Over here. Thank you very much, Paul, and it's great to be back in Lismore after so long, almost 400 years. So I'm going to take you through a short account of my life and some of my work, and we're going to recreate it like we did back in the day when people were unconvinced about the experimental philosophy, and there was a lot of doubters and skeptics. So it was very important to perform experiments publicly so people could witness them. So we're going to do some of that. But first I'll tell you a little bit about myself. So yes, we're going to go back to the 17th century, a time when we can look back and say we can identify modern science as evolving then. But of course, when you're in the middle of change, it's not so obvious. In fact, in the universities, most of the prevailing philosophy was Aristotelian. So a mere 2,500-year-old philosophy. It stood the test of time, but we believe that no matter how long something is believed, so the example I used was with a coin. It doesn't matter how long a coin has been in circulation. It doesn't matter whose head is on the coin. It doesn't matter how many people have used that coin. The only thing to tell if that coin was true or not is the chemical assay. Okay, so, and there was a lot of very dodgy coins going around in that long time before Bitcoin, of course. So here we are, ready to go. The cleverest thing I did was to choose my father wisely, and that was Richard Boyle, the great Earl of Cork, whose main seat was in Lismore, the beautiful ornament of Lismore Castle. And my father came to Ireland with £27 in his pocket and rose to become the richest man in Ireland, and at a time the richest man in Ireland and Britain. How he did that is something we don't talk about. Suffice to say, he worked for the Crown in redistribution of land from the restless natives had to have their land confiscated and sold to good Protestant settlers who would civilize the country and improve the country. In the process, he ended up with a lot of land himself, and it was said that you could walk from Dungarvan in Waterford to Killarney in Kerry without straying from his land for more than a few miles. Okay, so he married Catherine Fenton, my mother, and they had 15 children. I was the 14th child and the 7th son. So I wasn't going to inherit the titles, but I was going to have all that bother of obligation to running a family. But it meant that I had enough money to spend on my science. My father was known as the Great Earl of Cork. My mother, unfortunately, died. The Great Earl died during the wars here of natural causes. But I was fostered out into the countryside, and at the age of 4, I was called back to the castle. The following morning, I was summoned to meet my father, and he informed me that my mother had died. So I was brought back to the castle to live. I lived there for only 4 years, and in the castle at the time was my older sister, Catherine. And I think, we'll just talk about this tomb here. So this is the tomb of my mother. It's not actually, sorry, it's a monument to my mother at the back of St. Patrick's Cathedral in Dublin. And if we go on, we'll see this is my mother and father represented, and this is me down here. And my sisters are here. You can see they're all wearing ermine to show that they had married peers. And my brothers, in turn, all became ennobled, apart from me. My sister Catherine, who was one of these here, was living in the castle when I came back to the castle. And this is my sister Catherine. So Catherine married Richard Jones, and he subsequently became the Viscount Ranelagh. So Catherine was then known for in posterity as Lady Ranelagh. And I think she was due to meet me here. Oh, please welcome my sister Catherine. So if we go on, and Catherine, she in many ways led the life all expected of a woman at the time. If we just go back a little bit first. So she led the life of a woman, but also led an intellectual life as well. And she was part of a circle called the Hartleap Circle of intellectuals in London. And they were very much connected with the Commonwealth, which came in useful for our family. Our family ended up on the right side every time. So if we go on, I was only kept in Lismore for about till I was 8. Then I was sent to Eton until I was 12. So Eton at that time was a school for the sons of very wealthy people. I don't know if it's changed yet. So I only stayed till the age of 12. So 4 years is enough schooling for anyone. But actually, I moved to Stallbridge House for a little while, and my father engaged a tutor, Isaac Marcombe, and we went on myself and my older brother Francis, who was 15, so he was quite grown up. He got married at the age of 15, and then we were immediately packed off to the continent for a tour of the continent. And if we go on, we can trace our path. Oh, before that, yes, let's look at what we learned when we were in school. We didn't learn anything the sort of science people learn today. As I said earlier, we defer to Aristotle for answers to most things about the natural world. So if we proceed, we can get some interesting teaching from Aristotle, who believed everything was made up of 4 elements. And he also believed, if we go on, there are the 4 elements, fire, air, water, and earth. We won't dwell too much on those. But what he said about falling objects is interesting. So if we go on, we'll see what he has to say. And just heavier objects fall faster than lighter objects. And that makes a lot of sense to us. We all realize that makes sense. And there we are, lucky to have a film made at the time, documentary evidence. So we went on a grand tour. We went to France, Geneva, and on to Italy, to Florence, Venice, and Rome. When we were in Florence, I learned about Galileo, and I subsequently read his books. And when we were in Florence, if we move on, while we were in Florence, Galileo died, and that had gave me quite an interest in Galileo. But this is what Galileo did. Here he goes. Galileo liked a lot of attention, by the way. So Galileo had a different idea that all objects fall at the same rate. And if we go on, there. Okay. Now, it's interesting, this was kind of contested, and people said, of course, they don't. What about a feather and a hammer? And Galileo had an answer to that. See? Feather, hammer, different rates. So what is Galileo talking about? And Galileo said that's because of air resistance. If they were in a vacuum, they'd be the same. And of course, the professors immediately were able to say, well, that's nonsense because you can't have a vacuum. Why can't you have a vacuum? Because Aristotle said you couldn't have a vacuum. So then there was a war in Ireland. We won't go into the unpleasant details, but I eventually made it back. There was also a war, the Civil War in England, but I made it back eventually and found out that my father had left me Stallbridge House, and I started my chemical experiments in Stallbridge House. So at the time, chemistry was had a few lives. One was alchemy, one was trades, and the other was pharmaceutical recipes, mainly plant-based cures.
At the time, women tended the physics garden, where they worked with and grew plants and herbs for medicine. And we circulated these recipes or medicines right across Europe. One of the medicines that we came up with was from violets, where we made the syrup of violet, which was used to treat stomach ailments. However, my brother discovered that there was another use for the syrup of violet.
Okay, so we take two glasses of unknown liquid. Could be water, could be some sort of poison. The alchemists tended to use their senses, as did most philosophers at the time. So we would sight. Hearing is not really much use in this case. We would have smell and, of course, taste. A lot of alchemists died young. But here we have our syrup of violets. And let's see what happens. We put our syrup of violets in here. It's pink. And and we put it in here. Very strange. Well, it tells us certainly that there's some difference here between these two. And the difference is that this is acidic, this is basic. Okay, so this is something that every pupil does, every young student in secondary, now in primary school will do. It's called an acid-base test, and this is an indicator. Now, this is so commonplace and so fundamental in chemistry that nobody ever thinks to ask, where did it come from? So it actually came from Robert Boyle. He coined the term analytical chemistry, and he had, so that was one of his very, very practical contributions to chemistry. Now we're going to look at some of, if we move on, yeah, so that's also flame tests. Different metals give different colors when burnt. Don't try it at home. So I wrote this book, The Sceptical Chymist, or Chemical Physical Doubts and Paradoxes Touching the Sphagerous Principle, commonly called hypostatical, as they want to be proposed and defended by the generality of alchemists, whereunto is promised part of another discourse relating to the same subject. And say that's only the title. So I must admit I was, why use one word when you can fill a page? So this book is a dialogue between people representing the different main philosophies. So Aristotelian, the four elements, Paracelsus, which was the main theory guiding people who were making medicines and chemical medicines, very influential, of course, wrong. And then Boyle, somebody representing Boyle himself. And Boyle, so they're arguing, very like other books of the day, whether it be Galileo's discourse or indeed probably the most popular book of the era, The Complete Angler, which was also in that style, a conversation between a hunter, a fisherman, I think there was somebody else. And so in the book, I amass evidence for the corpuscular theory. So to show that everything could be explained by the action of corpuscles. So tiny little particles that everything is made up of, and they only vary by size, shape, and motion. And all qualities and behavior can be explained by the difference in size, motion, and shape of those corpuscles. I didn't call them atoms because the word atom was around, but it had unpleasant associations with Epicurus and atheism. So we made a kind of the corpuscle is a Christian atom. So this book enormously, and the other work, as I said, that chemistry was the realm of the alchemists, who were largely a lot of charlatans, even though there was serious alchemists. It was trades, which of course is even worse, and it was associated with medicines. So this book drew those together, gave chemistry a theoretical underpinning, and established chemistry as a field of philosophy that gentlemen could actually explore. I did work on many different areas. Cold, for instance. Our progress really on cold was limited by our thermometers. Our thermometers were so everyone used different configuration. They couldn't be compared with each other, and I'm kicking myself now. I never thought of having a vacuum in the thermometer and having invented the modern thermometer. But we used primitive thermometers. Wrote on colors and light, the spectrum, all of that. And if we go on, there's some of the thermometers. Now, this chap, Torricelli, if we just run on, this should, he filled the tube with mercury. The tube was sealed at one end, and he did a strange thing. He put it into a bowl of mercury and took away his finger. And the mercury fell down, but it stopped. And the question is, what's holding the mercury up? And the second question is, what's up here? What's in the top? Could there possibly be nothing? So this caused a lot of arguments. And if we go on, the weight of the air. So people like Pascal said it was the weight of the air. Aristotle, of course, said there was no weight in air, so it was a minority kind of opinion about the weight of the air. Common sense kind of tells us there's no weight in air. In 1654, the von Guericke, a very important German scientist and inventor, created an air pump, and he evacuated two copper bowls, and stuck them together, and 16 horses couldn't pull them apart. So this was, again, is that the weight of the air really pushing them together? So when I heard about that, I teamed up with my assistant by the way, I moved to Oxford because it was more conducive to the philosophy to be mixing with other philosophers. I wasn't part of the university. Remember, I had 4 years of schooling behind me. I didn't have any need for that. Anyway, I teamed up with Robert Hooke, who built a mechanical genius who built this air pump. But the idea was I wanted one with glass receiver so we could observe what was happening. Von Guericke's hemispheres and air pump was really a one trick, whereas we wanted to be able to do some other more serious scientific work. So we get the balloon first. Okay, so we have a huge balloon here, and we'll put it in to the receiver. It'll take approximately 20 minutes to pump out the air using the crank handle. So if we go now, and we observe what's happening to the balloon. Now, of course, it could be some form of magic, some form of psychic powers that I'm using. It could be that that balloon was going to grow anyway. There could be something in it, something in the nature of the air. So these are things, you know, it's not necessarily obvious what's happening. So we have to vary things. So maybe we let the air in. If it is something to do with the pressure of the air, maybe when we let the air in, it might go back to the way it was. Yeah, so there's probably other explanations. There's a lot of other explanations you can come up with. But we'll do the candle next. No. Do it now. Okay, so did a lot of different experiments. So the candle. Now, you guys probably know what's going to happen when we withdraw the air from the candle. Okay, let's see. Now, you might see the smoke doesn't rise because there's no air to displace. Now, there's less and less oxygen, so the flame is going blue. And after about 20 minutes of pumping, it's gone. Okay? So, that's not a big surprise to you guys. I didn't notice a round of applause. So I assume everyone knows that. Again, it's so commonplace, so taken for granted. Robert Boyle from Lismore was the first person to show that. Another thing was basically being a good scientist driven by curiosity. I basically put anything that would fit into it. That includes mice, rats, a duck, various birds, anything that would fit in, snakes, frogs, and even, what's this? Anyway, here we're doing it. This is, no, help. And let's see what happens. Seems to be fine. Yeah, seems to be fine. Maybe we better abort the experiment. Now, we don't do these experiments anymore because we know the answer. But it wasn't appreciated, because if you think of it, if somebody drowned or somebody was strangled or that, there could be lots of other explanations for why they died. This was the first time it was shown that air was necessary. And we did a few things where if we let in the air fast enough, the animal would revive. But after a while, I got a bit squeamish and believed that we didn't want to, understood that animals suffered, as Bill was explaining yesterday, so we didn't do much more of those experiments. But I did make the connection to say there's something similar, there's some connection between respiration and combustion, and we know that to be the case now. Okay, have we put enough in this? We've done enough.
Yeah.
Okay. So what we might show next is what happens when we increase the pressure. Okay, now this is a very dangerous experiment because we're dealing with high pressures. So I'm going to get Robert Hooke here, who's now Robert Hooke. Quick change, yeah. Okay, put your hand there, will you? Just, and I'll go over here, and we'll see. So this is, we can't increase the pressure on the receiver because the lid will just lift off. So we'll do it here. We'll see what's the. Okay. Let me just turn this around. Sorry. We've had a equipment malfunction. Now, of course, we didn't have balloons back in the day. We had lamb's bladders, were the usual go-to thing. They weren't used at children's parties much, but they were used for our scientific work. Right, let's see, will that work? So we're pumping air in to the vessel, and can we see what's happening to the?
Oh.
Okay, doesn't matter.
Okay.
Getting smaller and smaller. Strictly speaking, it should disappear if we. Oh, okay. Well, we're stuck there, but we've seen the effect, haven't we? That as we add pressure, the volume decreases. When we had the balloon here, when we decreased the pressure pushing on it, the weight of the air in the balloon was able to spread out more and take up more space. So that became, if we move on for a few. Okay. So those experiments, the air experiments, were published in 1660, touching the spring of the air. And there was 43 experiments in it. Very, very famous, very important. Bill yesterday described it as possibly the most important book in science. It's certainly very readable. And it's written in great detail, so other people could replicate these things in the comfort of their own mansions around the place. So if we move on again, this is a famous painting. Bill showed it yesterday, I think, the bird in the air pump. We'll move on. This is an account of frogs in an air pump. No, that's snakes, frogs. We decrease the pressure using the pump. The volume of the balloon increased. If we go on next, and we'll see if we increase the pressure, we've just seen the volume decreases. And we investigated that idea even more closely. And this is the experiments. These are the original Boyle's law experiment, something that all leaving certs in physics or physics, I think, have to do. And generally they don't like doing taking measurements and doing tables and that. It'd be far more fun just to look at what's happening, just to experience the phenomenon and develop an intuition about the phenomenon and not to be worried about these sort of details. But anyway, this was a law that showed that two things in nature, pressure and volume, were connected by a mathematical law. So, and it's an inverse. So we double one, the other halves. If we have one, the other doubles. So here we are. If we go on again, and if we plot it, this is what we get. This is the typical curve showing an inverse law. And we'll go on because that's not on the exam. See if this will play actually. That won't play either, but that is on the moon. Do you remember we were talking about Galileo and the hammer and the feather? They tried it on the moon. And do you know what they said? At the end of this clip, we won't be able to hear it. The previous clip is actually Brian Cox in the world's largest vacuum chamber, and he didn't know much about it either. But at the end of this, he said, "Oh, I guess Mr. Galileo was right." And they thought so Brian Cox thought he proved it a few years ago, but in fact it was done on the moon 50 years ago, let's say. Well, in fact, it was done 350 years ago. You hold that there. Our feather, I'm not putting a hammer in here, by the way.
No.
Yeah, that's fine, just hold it there. Now, so we have a tube here.
No, it's this one.
No, just. What are we doing there? Yeah, okay.
Got it?
We just wait till. Let's say, okay, we're nearly evacuated. Okay, so we remove the air from the tube and we see what happens to the feather. Can you see it falling? I'll bring it out to the light better. Now, of course, I'm doing this backwards. I should have showed you the feather with it falling in air. Okay, you can do that. Okay, and you take that for a second. Okay, so we'll see what it looks like. Okay, so we did it backwards. You're amazed at how slow a feather falls now. So anyway, and to make matter, of course, seeing Brian Cox and seeing astronauts is a bit irritating. But what's more irritating is these tubes now are referred to as Newton's tubes. So he took credit for he did a lot, but he took credit for an awful lot as well. Okay, so if we move on. So my philosophy was, there was a lot of competing ways of looking at the world. The main way was Aristotelian, but there was a lot of others. But the mechanical philosophy was the belief that everything in the world was caused by, or could be explained by, the interaction of matter with other matter. We had people like Descartes had a rather extreme form of it to try and to save that theory. He had convoluted ideas about vortexes and everything, and he believed that you couldn't have a vacuum, so we had all these vortexes in nature, and even things like magnetism, of course. We still have a lot of problems with action at a distance, so the mechanical philosophers didn't like action at a distance, thought that everything had to be some sort of direct interaction of matter. There was theories like, I think it was Descartes himself, thought that magnetism was these streams of screw-like particles coming out of a magnet and screwing into the iron or whatever and winding it in. So rather imaginative, and it was very, I mean, I don't know if there any way even now to test that hypothesis. But anyway, that's the mechanical philosophy. Linked to that is a corpuscular theory. So my corpuscular theory, as you can see, is very close, or it's a very primitive atomic theory. And then the key thing, experiment, the experimental philosophy. Descartes believed in reasoning from first principles. Galileo did a number of experiments, but a lot of them that he claimed, like the Tower of Pisa, and that, very unlikely that actually happened. So they were thought experiments. The actual experiment, the idea of doing experiments to create knowledge, but also to make sure those experiments are witnessed, that they can be repeated by other people, so reproducibility. That unsuccessful experiments should be reported on as well. These are all key parts of modern science. And, you know, I think oftentimes we think that progress is obvious, that it was obvious we would arrive where we are today. But actually, at every step of the way, as Emma said, there's all sorts of different options in every moment. And to say that it was obvious, that particularly I think experimental philosophy winning out, and a lot of that was about particularly the air pump experiments. They were absolutely sensational in the day, and the Royal Society put on the air pump experiments anytime there was visiting dignitaries, people going to London. If you were lucky, you could get in and see the air pump experiments. But it meant that people could witness it. You weren't just reading about it, and that was very important in the acceptance of science. So just to say that I was born in 1627, so next year I'll be 400 years old, and we're hoping that there'll be we manage to encourage a lot of people around the world to have celebrations, and we'll be coordinating them through our website, and we'll be running our own things too, of course. But next year, so the Boyle Summer School and the Boyle Winter School will be really important. So, thank you very much for your attention.